So I hope few of you might have attempted those problems. Okay. There are two problems. One was from synchronous generator, and it was very simple because the resistance is neglected. As the resistance is neglected, your power output will become equal to power developed. Okay, because we have seen the power flow diagram also. Let us go to that question. So this was your question, right? We have 40 kVA generator, 220 volts, 50 Hz, 4 pole, 3 phase, Y connected alternator, and the synchronous reactance is given only 0.08, and the armature resistance is neglected, right? It is negligibly small, so we can neglect it. So I can write Ra equal to 0. Okay. So when Ra equal to 0, your copper loss, that is Ia square Ra will be 0, right? So as the copper loss will become 0, from the power flow diagram also you can check it. Your PD equal to P out. Okay. So now if you know the P out, then you have to take the rotational loss. Very simple problem. Rotational loss is 0.05 into PD, right? So P out is how much? Can anybody tell? How much is P out? 40 kVA. 40 kVA is output power. It is the apparent power, right? Real power is 40 into cos theta, right? That is the power factor is given 0.866. So whatever it will come, you can write it. And then PR will be 0.05 into P out. That is equal to PD, so you can write here also PR, right? Now what else is asked? Power factor, power angle and efficiency. So efficiency we know, efficiency is P out. P out is given by P in. So P in is how much? P out plus PR. Because your copper loss is 0, so this P out plus PR is sufficient, right? Okay. So you can find P in also. Now substitute P out, P in, you will find efficiency. It is very simple problem, right? And now power angle, how will calculate? Power angle is the angle between EA and VA, right? So EA is, you know, EA is how much? It is VA plus J of IA XS. XS is given here 0.08, and IA, you know, IA you have to find it out. Just multiplying with IA. IA is a vector quantity here because IA has an angle of, it will be IA magnitude, and angle is 30 degree, right? It is 0.866 leading means 30 degree leading, right? So IA you can find from this kVA rating. Very simple, just by multiplying. IA will be, how much it will be? IA will be 40 into 10 to the power 3, 40 kVA by root 3 into 240. This is IA. This is the magnitude of IA, right? And just by putting here, you will find IA angle 30 degree, and then just substituting here whatever angle you will get EA, because here is VA is a reference phasor. This is your reference phasor, right? VA. So whatever angle EA will make or you will find from calculation, that is the rotor angle. Okay. So how much you got the rotor angle? Can anybody remember yesterday? How much you got? I got 2.83D. Anybody got this? What? Cos of? Cos inverse theta. That will give me theta, right? Cos inverse 0.866L, it will give me
87 37 sir.
So you do it once again, okay? Whatever the process I told, you follow it and do it. Okay, why you are coming late? Question number 2. This is also a very simple problem. If you know the equivalent circuit, you can do it easily, right? So here it is given long shunt, cumulative compound motor. Long shunt you know very well, right?
Yes.
Very good. So this is shunt, right? And your terminal voltage is 230 volt. Okay. And it is rotating at 1800 rpm. Shunt field resistance is 460. That is RSH, I can say 460. RAC is equal to 0.2 and RA is equal to 1.3. Okay. Now the full load line current is 10.5 ampere. Here it is 10.5 ampere is flowing. IL is 10.5 ampere. Okay. Clear? Now what will be IA? IA will be 10 ampere, right? Because here it is 0.5 ampere is flowing. Okay, in field circuit. 230 by 460, it will be half, right? Okay, 0.5 ampere here in the field circuit. So remaining will flow in the armature circuit. 10 ampere. Correct? This field is connected across the source, right? So 230 by 460. It is 0.5 ampere. So then 10 ampere is flowing in the armature circuit. Now you can do all the problems, right? This is very simple right now. So I hope you can do it, right? Everybody? Okay. So I don't think I need to do any further explanation because... So here we have two parts. This problem had two parts. So in the first part you have to compute the efficiency with 1800 rpm, right? And 10.5 ampere load current. Now in the second part, when the line current rises to 15.5 ampere with increased load, now the load increased on the motor and the line current increased to 15.5 ampere and there is a 20% increase in flux in the motor. It is because of the series field winding. Because as the armature current will increase, the flux will also increase. So the increment is mentioned here 20%. Now I have to calculate the new speed of the motor and the efficiency. So new speed you can calculate from the formula, like I can say EA1 by EA2 is equal to 5P1 omega 1 by 5P2 omega 2. Just substituting the values you can find omega 2, the new speed, right? Okay. Similarly you can find the efficiency as well, as for the first step, right? Okay, so it is very simple. So I hope you can do more problems from books. Any book you can take, you will find a lot of problems in the machines course. Okay. So please practice. We'll have next quiz sometime, maybe I'll tell you the date. Okay, so today we'll see the parallel operation of synchronous generators. What you are doing in your lab, that is actually you are synchronizing the generator to the grid, right? So the grid you are telling that is infinite bus. So what is infinite bus? Infinite bus means the voltage, the phase angle, everything remains constant, even frequency, right? Voltage, infinite bus. Voltage and frequency is constant. Okay, so that we call the infinite bus. Okay, we are connecting, when we are parallel operation of generator means both, there are many generators together, they are connected to a infinite bus. That means if we'll see our power grid acts as a infinite bus where there are many units, they are connected together and they are operating in parallel. Okay, sometimes some generators operating on floating mode, sometimes they are supplying to the load of the grid, right? So therefore, what is the necessity of this parallel operation of the generator? Why it is essentially required? Why we are not operating a single generator and we connect loads? Because as we are increasing the loads in the system, like suppose let us say we'll consider the IIT Patna campus. In this campus we have certain load and we can fulfill with certain generators. But suppose there are many loads connected, like suppose we'll consider the whole beta. There are a lot of loads, right? There are many consumers, many industries, there are many commercial sectors. So when they want power, of course, they can also have their own generator, they can supply to their own load, right? But what is the necessity of connecting together generators? The important necessity is the reliability of the system. Okay? So when we interconnect different networks and the generators come parallel, they operate in parallel, they will maintain the reliability. Suppose in IIT Patna we have certain breakdown in the generator, then we can take power from the other sources if the generators are connected in parallel, right? Similarly, they can also take power from us. So likewise, this whole network, we can say in India also we have different regional networks, 5 regional networks. In a particular region, we have many generators that are connected to the grid. Okay. And finally, all these regions are interconnected through the tie lines so that they can exchange power between different regions. Okay. So this is how we can maintain the reliability of the system more prominently, right? So therefore, parallel operation of synchronous generator is very much essential for the power system to operate. So what is this parallel operation? So there are certain requirements for the generators. It should be maintained when it is connecting to an infinite bus. Okay. What are those requirements? First is the line voltage of the incoming alternator must be equal to the constant voltage of the infinite bus. So before connecting a generator to the grid or to the infinite bus, it must be ensured that the voltage magnitude of the generator is equal where the point of connection or the point of coupling where we want to connect, right? Next is the frequency of the incoming alternator must be exactly equal to that of infinite bus. Okay, whatever frequency the infinite bus has, like a 60 Hertz grid, we cannot connect a 50 Hertz grid. It is not possible. So therefore, we need to match the frequency of the infinite bus with the generator frequency, supply frequency. Then the phase sequence of the incoming alternator must be identical to the phase sequence of the infinite bus. What is this phase sequence? You have performed your experiment, right? All your experiments are over today? Oh, very good. Manavendra has completed. Congratulations. So all your generators, right, having 3-phase, and infinite bus has also 3-phase. So this 3-phase, like he mentioned, RYB. This is the sequence. Okay. And this sequence can be changed, like I can say RBY or I can say YBR. Many ways I can change the sequence of the phases, right? So this sequence of, we can say the sequence of the generator, phase sequence of the generator should be equal to the phase sequence of the alternator. If it is not, then we cannot connect, because the phase difference between the two phases should be equal, right? So how will ensure that these three things are maintained? So what method you are doing? What method you are employing? Dark lamp method. What is the process here? Dark lamp method? Huh? Now when you close the switch, when all the lamps are dark or bright? Huh? Dark, right? When all the lamps are dark means? Huh? No, they are in sync of course, but what it mean? All the lamps dark means, suppose a bulb is there and you are giving a connection to it and it become dark. That means? Dark means? Huh? Very good. The voltage across the lamp is 0. Okay? When the bulb is 0, it is not glowing, it is dark means the voltage across the bulb is 0. And at that moment the voltage across the bulb becomes 0. Why it becomes 0? Because it is connected in series with two networks. One is your generator, other one is your grid. And when both the voltages and phase sequences are same simultaneously, obviously the bulb will be dark. As soon as there is a mismatch, it will glow. Because the voltage drop across the bulb remains somehow with some magnitude or with some phase difference, therefore it glows, right? So when it matches the grid frequency, grid voltage, magnitude and phase sequence, then it will stop glowing. Because the voltage across the bulb becomes 0. Okay? Now this is not a dark lamp method. Also there are many methods we can use. This is a bright lamp method we call it, right? So the connection is a little different as you do in the lab. In the lab you do the connection exactly with R phase to R phase, Y phase to Y phase, and B phase to B phase. But here you can say the A phase is connected to A phase, B phase is connected to C phase here, right? And C phase is connected to B phase here, right? So this is called the bright lamp method. And sometime in order to check the correctness or the accuracy, improve the accuracy of this method, what we do, we put a synchroscope here. Synchroscope is not there in our lab, but synchroscope actually exactly shows the sync between the generator and the infinite bus, right? So what is this synchroscope? You can see here. This is your synchroscope, right? When this needle of the synchroscope is exactly at the middle, that means it shows it is actually sync. That means the voltage magnitude, frequency and phase sequence, they are same, right? When it is moving towards right or in clockwise direction, your generator is fast. The rotation is fast, right? The frequency is more of the generator. When it is slow, it is go towards counterclockwise, okay? Then the generator speed is low, okay? So now, this is one alternator which is already connected to the infinite bus, that alternator A, and alternator B is connected later through the bright lamp method. Here it is shown, and it is connected to the infinite bus, right? The process already you know what you are doing in the lab, the same process, but here the approach is little different, right? Okay. So now we can see this is the output power. We know this output power PD, or we can say this is output power is equal to power developed when RA is equal to 0, right? Already we know this. This is 3EA VA sine delta by XS. We have derived this in the last class, and that is also of course equal to 3VIA cos theta. So what is the difference we are seeing here? These two equations. One is written in the form of load current and voltage, terminal voltage, and another was written in terms of induced EMF, terminal voltage and the power angle, right? Here theta is the power factor angle and delta is your power angle, which is the angle between EA and VA, right? Now, suppose, let us say, because your field is constant, we are not changing here the field, so your EA will remain constant, right? and your terminal voltage will be constant because the generator is connected to the infinite bus, and your synchronous reactance at a particular operating point it will remain constant, right? Okay, particular loading condition specially we can say. And then if we'll say that EA is varying, so EA will vary. How it will vary? When will vary the IF. Okay, when your field current will vary, let us say we are varying the field current. Now we'll see the impact, what is happening in the generator, and that also you have done it in your lab. Have you done this? Varying the IF, you have measured the IA, right? Okay, and you plotted it. Okay, IA versus IF. What type of curve you got? V curve, right? V curve. But your curve was not V. I was saying. You have to rotate the laptop, right? Okay. So V curve means it should be IA versus IF, right? That means we are varying IF to see how we get this V curve. Just a simple explanation is given here with the phasor diagram. Now your VA is constant, okay, and if we'll see XS is constant and your EA sine delta will remain constant because EA is varying. Of course EA will vary, but your EA sine delta will remain constant in order to make this constant, right? So this VA and XS constant. So in order to maintain this EA sine delta, right? So your delta will vary as per your variation in the IF. As you change the field voltage, your delta will vary. Field current, your delta will vary, right? The first we are seeing here VA, where we can see the IA is here, the dark line, right? And we have here it is plotted EA because VA plus JF IA XS is equal to E, right? Now as your field current is varied, suppose let us say your field current is varied and your IA has changed, or the load is changed to this. Now I can say the load current is changed to this, then your JF IA XS will be here and EA will be here, right? Okay, so EA will also vary simultaneously as you change the field current. Similarly, from this figure we can see as your output is constant and VA is constant, cos theta, IA cos theta will also remain constant. As your P out is constant, so your VA is constant, so therefore your IA cos theta will be constant, right? Similarly, from the first equation also, as your VA is constant, XS is constant, so EA sine delta will remain constant, okay? So therefore, considering these two equations, that is IA cos theta is constant and EA sine delta is constant, we can see here it is plotted EA sine delta and here it is IA cos theta, right? Now as you change the load current and the field current both, you will find that your delta is varying, right? As your delta is varying with, like when this is the IA, this dotted line, or you can say dashed line, so your EA will come to here, right? And your delta will increase. Similarly, if your IA now will consider dotted line here, right? So it is now leading, right? So then your EA will come to here. When we add VA plus JF IA XS, your EA will come here and your delta will increase more. So up to what point we can increase this delta? Can you tell? Up to what point we can increase this delta? When your IA, suppose say it is leading 90 degree, then how much we can, what will be delta value? Suppose your IA is here, okay? Up to 90 degree we can increase the delta value, right? Yes. So delta value we can increase up to maximum up to 90 degree. Of course, this will also you will read in a power system course why delta max will be 90 degree, right? Gradually you will read. So this will be the curve we will find. As we see here, your for different power outputs PO1, PO2 and PO3, the V curve is plotted. Okay. So now for PO1 we have seen from leading to lagging as it moves. Okay, at unity power factor this will be minimum, your IA will become minimum, because here we can see at unity power factor your IA will be here and this is the minimum value of IA, right? Okay, so therefore at unit power factor your IA will become minimum, and then in the under leading and lagging condition your IA will increase gradually. Okay. So therefore we got this curve. When we plot IA versus IF, we got and it is prominent from the phasor diagram also. You can see here, as we decrease the phase angle of IA, right, that power factor angle, and when it is unity your IA is less as compared to the increasing leading and lagging IA, right? So therefore we got U-shaped curve when we plot IA versus IF, and we call this U curve. Okay. Okay. So now we'll see the parallel operation of two synchronous generators, and little bit we'll do analysis how the load is being shared with two generators when they are connected in parallel. Here you can see here we have equivalent circuit of two generators. They are connected in parallel and they are supplying to a single load which is ZL, right? So this is generator 1 and this is your generator 2. The generator 1 is EA1 ZS1. ZS1 is your synchronous impedance, and similarly EA2 also, that is ZS2, having synchronous impedance ZS2. Now both are supplying current. One is supplying IA1, other one is IA2. Now if you write the equation, your IL will be equal to IA1 plus IA2. Okay. Now you can see the equations here. So if we write the terminal voltage equation considering both the generators, so for first generator it will become EA1 minus IA1 Z1, and for the second equation EA2 minus IA2 Z2, which will be both are equal and which will be equal to IL ZL. Okay. Now your IL will be equal to IA1 plus IA2, very simple, right? Now I can write EA1 in terms of IA1 ZS1, right? So EA1 will become equal to VA plus IA1 ZS1. So instead of VA I can write IL ZL, right? So therefore I can write IA1 into ZS1 plus ZL plus IA2 ZL, because IL I can substitute here as IA1 plus IA2. Okay, after substituting I will get this expression. Similarly I can write EA2 also. Okay, now from these two equations if I will segregate and I will try to find IA1, I will find the expression this IA1. Just segregating IA1 and IA2, I will find this expression for IA1 and this expression for IA2. You can also try it, you will find the same expression, right? So both the expression, and now these expressions are expressed IA1 and IA2 is the current shared by the generator towards the load current, right? And it is expressed in terms of induced EMF, load impedance, and source impedance, right? Then I can find IL, that is the net load current, that is equal to IA1 plus IA2. Okay, if I'll add both the expressions, I'll find this. So this is how we can find the load sharing of two generators or maybe three generators when they're connected in parallel and supplying a single load, or there may be many loads, because loads are always connected in parallel. So we can put the loads in parallel, right? Okay. This is what we can find also VA, that is the terminal voltage in terms of induced EMF and other parameters, right? Okay. So this is the expression for VA. Okay. So this is all about your synchronous generator. We finished. So tomorrow onwards, next class onwards, we'll read synchronous motor. And synchronous motor will finish quickly, maybe 1 or 2 lectures. Then we'll talk about induction motors. Okay. Thank you very much.